So as I said, I think I missed one thing when I was talking about the Perron-Frobenius. So let me just go back to it. I'll just make a passing remark and then just move on because I think we are not um, going to spend a lot of time on that, right? So what I was saying was that just like we talked about the spectral properties of the Koopman operator, and then in the discussion towards the end, we said that the eigenfunction of the Koopman operators can be used as a change of coordinates to transform a nonlinear system to a linear system, and so that's like a good motivation for actually uh, looking at the spectral properties of Koopman. One could ask the same question as to what is the spectrum of the Perron-Frobenius actually tells you, okay, and what's the significance of that? Why? Because it's a linear operator, we can again talk about those eigenfunctions or eigenvalues. So one of the challenge with the spectrum of the Perron-Frobenius is that the spectrum is actually may not be a good spectrum. What I mean by that is in the functional analytical sense, the spectral could be a point spectrum. I mean, the spectrum could be like a distribution, like a delta distribution. Take a simple example. Let's say if I take a um, um, so one of the because this operator actually propagate densities forward in time, we can talk about what is the eigen, and this one can show that there is always one of the eigenvalues of this Perron-Frobenius operator will always be 1. There could be multiple eigenvalues 1, but there is at least one eigenvalue 1 for sure. And the eigenfunction corresponds to the eigenvalue 1 of the Perron-Frobenius operator tells you about what is called a steady state dynamics of the system. Okay. So, for example, let's say if you take a simple example of a scalar linear system, x dot equals minus x. Okay. X dot equals minus x. You cannot get any simpler than that, right? And for that one-dimensional stable system, you know what happens, right? Everything eventually gets attracted to 0, right? Because it's a globally stable system. Now you should put some initial distribution of points in that for that system and propagate them forward in time. What do you think will happen? All points converge to 0. So if you take any distribution, it will converge to 0, and that will be in the distribution sense, that will converge to a delta distribution, right? So it will be a Dirac delta function at the origin, which is so the steady state properties of a dynamical system is actually the information about the steady state properties of a dynamical system can be recovered from the eigenfunction with eigenvalue 1 of the Perron-Frobenius operator. Computing this eigenfunction is a challenge though, because given any complex dynamical system, finding where the steady state dynamics resides or how the steady state distribution of points is actually is complicated. Like going back to the example that we did yesterday, the logistic map example, right? I told you that if you look at a pointwise behavior of that logistic map, it is very complicated, right? But if you look at it in the function space, then everything converges to a nice simple function. And what I did is, and I think this is a very easy exercise that you could do, just go on ChatGPT and ask it to write a MATLAB script for propagating distribution of points for a logistic map. Right? So write a simple MATLAB code. I mean, you don't have to write it. Ask ChatGPT to write it. Simple MATLAB code for propagating a distribution of point for a logistic map. Okay, and run that MATLAB code. That code is written exactly along the lines of what I described yesterday. Put some distribution of points, bin the 0, 1 set into some n boxes, pick some m initial conditions, and construct a histogram as for forward in time. And it'll see that, as I was telling you, that it'll converge to a nice function for after sufficiently large time. Now that function to which that things are converging to, that is precisely the eigenfunction with eigenvalue 1 of the Perron-Frobenius operator. Because that's the steady state distribution. And for the logistic map, no matter what initial distribution of point you start with, it will always converge to that distribution. What that tells you is that the Perron-Frobenius operator for the logistic map has only one eigenvalue 1. If there are multiple eigenvalues 1, that means it has multiple steady state. For example, if you take another simple system, let's say x dot equals minus x plus x cubed. Okay, minus x plus x cubed. So it has a stable equilibrium point, or maybe I should make it a little more complicated. What I want to actually convey you is the fact that let's say you have a dynamical system which has two stable equilibrium points with their own domain of attraction. Okay. Now, how the steady state dynamics of that system will look like? So steady state dynamics of a system will look like the following, right? If you start within one domain of attraction or domain of attraction of one equilibrium point, then everything will converge to that equilibrium point. Now, if you start within domain of attraction of other equilibrium point, then everything will converge to that particular equilibrium point, right? So steady state dynamics of that system basically depends upon where you start. And it will consist of two different equilibrium points. Now, if you look at a Perron-Frobenius operator for that system, what now you can say is that there will be that Perron-Frobenius operator will have two eigenvalues 1. Each eigenvalue correspond to the one steady state distribution, one steady state. And the eigenfunction correspond to the eigenvalue will tell you what that equilibrium point is, or where the steady state distribution, where the steady state dynamics resides. Make sense? So the Perron-Frobenius operator for that system will have two delta distribution. One delta distribution focused on or concentrated on one of the stable equilibrium point. Second delta distribution will be concentrated at a second equilibrium point. And then that Perron-Frobenius will have two eigenvalues 1, basically telling you that it has two steady state distributions. So that's actually one of the properties of the spectral of the Perron-Frobenius operator. And for deterministic system, most likely you will get this eigenfunction with a delta distribution, Dirac delta, right? Of course, for the logistic map, that's not Dirac delta, even though it's a deterministic system, because the system is chaotic. So the distribution is not at one point, it's sort of everywhere, as I showed you. So anyway, I mean, that's the significance of the eigenfunction with the eigenvalue 1 of the Perron-Frobenius operator. There are other eigenfunctions because it's an infinite dimensional operator. It has other eigenfunctions with other eigenvalues, and those carry some other information. Like if you have system with limit cycles and like a bistable behavior and so on and so forth. So those other informations are there in the other part of the spectrum. Okay, but just to sort of the most important one is the one with the eigenfunction with eigenvalue 1, and that has tremendous application in dynamical systems. Okay, and I will tell you later on when it comes to control, this Perron-Frobenius actually has some very interesting properties, which actually comes in very handy when you try to design controllers using this operator framework, right? As I was referring to, the main advantage is that if you formulate the control problem in this in the Perron-Frobenius, you actually get a convex. You sort of convert this non-convex problem to a convex problem. Okay, so more on that when it talks about the control. So what I want to talk about now is actually, I mean, and then sort of maybe again touching on this this path integral formula, going back to this connection, and this is sort of very not something which is sort of rigorously proved, but I'm just telling you based on like my experience, and I feel that this is something actually is a good opportunity to sort of do research and of course write papers and get PhDs. And we kind of touch upon this towards the end, saying that all these methods that are there in differential geometry when it comes to control or even just a system analysis is a very elegant method. It's a very beautiful method. One of the challenge with this method is that you cannot do computations, and the second challenge is that these are mainly restricted because it's a geometry. These are mainly restricted to low dimensional system, right? And the computation challenge mainly also occurs because of the fact that when it, like for example, let's say you want to construct this change of coordinates and a feedback linearization base control design, right? So those who have seen this, I think you have to compute a lot of Lie derivatives. Like you have to take a lot of Lie derivatives and then compute this change of coordinates. And typically, what you end up with, if you and all the examples that you have seen, textbook example, they will deal with like a polynomial vector field, and then you actually do all these computations, and then you end up with a change of coordinates which are all polynomials. Okay, and many times actually system may not be polynomial, and in fact the change of even if the system is polynomial, it is wrong to assume that it's very easy to show. And in fact, I could write it down. It is possible that this change of coordinates may not be polynomial. Change of coordinate may not even be a rational functions. Okay? And that's, I think, is one of the main challenge when it comes to computation, or translating some of the differential geometric ideas to do computation. And the reason I'm saying is because of the following. So if you look at this path integral formula, although my vector field is polynomial, this h of x is not guaranteed to be polynomial. I mean, of course, from this you cannot see it, but if you look at this complexity of this, there is an integral here. If I could actually solve this integral explicitly, which is not possible, you can compute it, may not be possible. You can compute this h as a function of x, given any x, I can find the h, because to compute it is fairly straightforward. So what do I need to do compute this? I just need to know the solution. I just need to know the trajectory of the system. Trajectory of the system is free. You can just simulate the system. So as far as computation is concerned, I can compute this very nicely. I may not find an analytical expression to fit this. Okay. So what you end up computing this may not be you may not be able to fit a polynomial to what you compute from this. Okay? Even though your vector field is polynomial. So given a polynomial vector field doesn't guarantee that the change of coordinates, which will actually convert this to maybe a linear system, is a polynomial. Okay? And that's, I think, is could be sort of some of the drawbacks when it comes to translating this differential geometry to computation. Anyway, so next thing which I want to talk about is the computation. Okay? So how do you actually compute these linear operators from data? Because I think that's what this is all about. So now that we have good understanding or fairly okay or understanding about what these operators are, what is the utility of these operators are, and what are the eigenfunctions information, what information the eigenfunction provides. The next question is, how do I actually compute this, especially from data? Okay? Let's say now you have a data coming from dynamical system. How do you actually use this data to construct the finite dimensional approximation of this operator? And again, now this is very, very active area. So my purpose in this is not to sort of I myself not familiar of what papers are written. I mean, I get all these papers every day, people writing papers on different ways of actually computing. So my goal is actually to just tell you the plain vanilla algorithm behind this approximation. And then there are various different, and I can point out to what are the different variants of this plain vanilla algorithm that one could actually further investigate, right? So behind the underlying principle behind this, the basic algorithm for the approximation of the Koopman operator and hence the Perron-Frobenius operator is the fact that these are linear operators. Okay. Now, what does that means is that these because these are linear operators, the way you approximate these, and that's actually a beauty of this, and that's why actually these are becoming more popular, because you don't need to know all this theory that I talked about to do computation. Okay, you could be fairly oblivious to all the mathematical details behind this Perron-Frobenius operator, but still you could actually compute these objects and use them for the purpose, whatever that is. Either you want to do some control design or you want to do some prediction. Okay? So the reason is that because the linear operators, the underlying algorithms which are used in the approximation of this are reduced to a simple least square problem. Okay? And that's why I was asking you about, do you know how to solve a least square problem? Because least square problem is easy, right? I mean, it has an analytical solution. It cannot get better than that, right? So that's the basic idea behind the algorithm or for approximating the Koopman operator, or at least the vanilla algorithm for the approximating the Koopman operator. Of course, there are a lot of variants of this. People have used all sorts of things now, like deep neural network from kernel methods, and I mean, kernel method is not that um, on the fringe, but neural networks, the tensor flows, and things like that. So anyway, so let me just explain this, the computation part. So the one of the most basic uh, algorithm is this, what is called as the DMD, dynamic mode decomposition. Okay. Um, so for those who know, okay, I don't, okay, let me just skip the theory, the history behind this. I could. So let me just get to the. So what are the ingredients? Uh, so let's say you have a time series data. Let's call the time series data X, which is X1, X2 to X, what I'm notation I'm using, X M minus 1. Okay. So what it is, so X1 is a vector, right? It's a measurements, assuming that you can measure all the states. And this is a timestamp. What I mean by that, there is a causality, right? There's a temporal. So X1 goes to X2, assuming a discrete time sitting. X2 goes to X3 and so on. So you have X1, so this is basically the trajectory. So it's done in discrete time. X3 and so on till Xn. Okay. I'm now putting them in a matrix, right? So the X is now a matrix. So if assuming that uh, Xk belongs to Rn, this will be a matrix of size n times m minus 1. Okay. Now you do a one time step delay. Right? You call that as X prime. So which will be X2, X3 to Xn. Just do one time step delay. Right? So this is the actual data. So the most basic algorithm, which is the what is called a dynamic mode decomposition, or DMD for short, what it's trying to do is that it is trying to find a matrix which best explains this data. Right? So you have a snapshot of a system at time 0 or 1, and a snapshot of a system at time 1. Right? What is the best matrix that you can fit to explain this data? Okay? This is now data in a matrix form. So basically, we are trying to ask the following question. Given X and X prime, what is the matrix A? X prime equals AX. Okay. X prime equals AX. So here A now is a matrix in n by n. Okay. Right? Because that's what it is. I think so. This is really not Koopman per se, right? Because I think the main idea of Koopman was you take the data and you go from state space to the function space. So we haven't gone to the function space yet, right? We just are still in a state space because data is still in a state space. But you can think of this as a function space, where the function space here is just the same data. I mean, there's this coordinate function, right? So anyway, so X prime equals AX. Now you can see this is basically, you can write it as a least square problem, right? So you want to, you may not able to fit this. So you write it as minimize over all A, X prime minus AX. This is a least square problem. And then you can find this. This is not the DMD algorithm per se. I'm just telling you the idea because I think DMD actually does compute this in terms of SVDs and so on, because for the computational, reduce the computational burden, because the kind of matrices that you will be dealing with in real application, where the M could be very large, right? Because you're collecting a lot of data. So you may not able to. So if I want to write down the solution of this, the A from the least square problem, this will have a, for those who, this is just an aside. So the least square problem will be something like, let me say something like AZ minus B, right? So this will be a least square problem. It's not in that form, but I mean, it doesn't matter. And then you write down the solution Z star as, how you write it? A pseudo inverse B, right? So that's the solution. And then the pseudo inverse is given by A transpose A inverse A transpose B, right? So this is your pseudo inverse of A, right? So that's the least square in a nutshell, basically, right? And that's what we're going to use here. It's just that now your Z is A, matrix A itself, or the entries of the matrix A. Your X prime is like a B, and your cal A is like your X. Okay. So the A star, which is the optimal, is given by X prime X pseudo inverse. Okay. X prime X pseudo inverse, because it's AX, not cal AZ. Okay. Does this make sense? Because I'm kind of relying on the fact that you know how to solve the least squared problem. Okay. Okay. Now, what is the pseudo inverse? I mean, you can write down the pseudo inverse as this will be X prime um, X transpose X inverse, and then X transpose. Okay. So this is your optimal A star. Of course, in practice, you may have to, actually right. So this is X prime is what, n times whatever m minus 1, right? And then this has to match the dimension. So it should be m minus m times n, so that the overall it should be n, right? So you will never compute A star using this formula, especially when you have m very large. If m is very small, then you can do this. But if the m is very large, then you have to use the singular value decomposition. So the way the algorithm works is that you first do a singular value decomposition. I have the details in the notes, so you can take a look at this. But let me just write it here. So the way you do that is you first do a singular value decomposition of X SVD, which is you write it as U sigma V star, where U and V are the unitary matrices, right? U and V are unitary matrices. Okay. And so with this, you can write down the pseudo inverse. So this is sort of dagger, right? So this is a dagger to denote the pseudo inverse, which is X transpose X inverse X transpose. So if you plug in this formula in here, what you get this to be V sigma inverse U star, right? So what you do is you take X, you do the SVD, so that then the inverse becomes V sigma inverse U star. I mean, you can carry out the steps. I'm skipping that, which is there in the notes, and then you write down your A star as X prime V sigma inverse U star, right? Okay. So this will be the formula for the optimal A star in terms of the singular decomposition of the data X. Now you can, once you have the A, you can find the eigenvalues and eigenvectors and then the eigenvectors will give you the eigenfunctions. So A W equals W lambda. So lambda will be the DMD eigenvalues. So I mean, I don't know how many of you are dealing with data in for your research or studies. If you haven't tried that, I would really encourage you to take the data and apply the simple algorithm and see what happens, right? Especially not the A part itself, computing the A, but computing the eigenfunctions or computing the eigenvectors and the eigenvalues. I don't know how many of you know POD, proper orthogonal decomposition, or SVD, which is a single variety decomposition, depending upon where you're coming from. In fluids, people call it POD. In signal processing, you call it SVD. In POD, especially from fluid dynamics application, the POD is actually used to find the dominant modes. So the dominant modes are actually dominant from the point of view of energy. So whenever you do proper orthogonal decomposition of a data, and then look at the eigenvalues and corresponding eigenvectors or eigenfunctions, let's call eigenvectors because you're dealing with matrices. Then when you do POD, the eigenvalues and eigenvectors will tell you what. So the eigenvalues actually are all positive because the SVD actually is a positive. You get all the eigenvalues positive. So the eigenvalues actually tell you, a dominant eigenvalue tells you and the corresponding eigenvectors tell you what are the dominant modes in the data range. So dominant from the point of view of the energy, right? Which modes carries most of the energy, so that you can actually now resolve. So one of the way of actually doing data dimension reduction, and I think that is also there in my lecture notes, which I didn't get time to cover, is this: how do you do data dimension reduction of a static data, which is there is no temporal. Right now we are dealing with all data which are temporal. There is a time involved in it. There is a causality involved in there, right? So if you're just given a data, if I want to do a data dimension reduction of a data, then the way you do that is using a POD or SVD, right? Or there are other nonlinear version of that, like a manifold learning or the diffusion maps and so on and so forth. But the plain vanilla algorithm again can be reduced to this POD or the SVD, either in the X space or in the lifted space. There, when you do the proper orthogonal decomposition, the proper orthogonal decomposition tells you what are the dominant modes in a data are. Now, then we can use the dominant mode to do a data dimension reduction, where you can actually project the data only onto the first few dominant mode, and that's how you get the data dimension reduction. That's the basic idea behind all the data dimension reduction algorithm, right? Either you do it in the kernel setting, or you just do it in the regular setting, right? Either you do it like a nonlinear version of that, or you just do a linear version of that. Now, sometimes what happens when you actually try to do the same thing, and this is what people have been doing in the fluid community, and that's how this DMD become very popular at one point. That's sort of telling you some brief history about this DMD. So if you try to use, let's say, fluid data, so what is the fluid data? So what you have is actually you're looking at you're looking at a movie, right? So you have let's say you're taking a snapshots of how the flow is evolving, right? It's basically like a two-dimensional. I'm looking at a two-dimensional flow. So you have the snapshots. If you don't want to think in terms of fluid, just think in terms of any other movie, like a person walking. Like if you're looking at those who do like biped robots or something, right? So you have a robot, like a human, which is walking. You're taking a picture, or the human has some sensors on it. You're taking a picture, and that picture is evolving, right? Now you can take that image and try to ask, okay, if I want to represent that image using very few dominant modes, how do I do that, right? What are the ways I could do that? One thing you can do is actually you can take all the different images, because think of this one image as one big vector. I can just concatenate that one image as one big vector, and now you have a sequence of images, right? Or sequence of vectors. There's a time there. You can forget about a time, let's say, for time being, and just take that as a one big matrix, like vectors put together, one big matrix, and then try to do a POD or the SVD, which is one and the same thing, and then find the eigenvalues and eigenfunction of that thing, just like what we did here, the SVD, right? Sorry, which is this, right? And then find the eigenvalues, eigenvectors, and now the eigenvector will tell you what are the most dominant from an energy point of view modes are in that movie, so that you can actually now project that movie, project the snapshot, the individual snapshot onto those dominant modes, and that gives you a data alignment reduction. What is happening in that problem is that the issue with that approach is that because you're not accounting for the temporal, the causality in the time series, and the system has really a temporal feature which has been ignored, you may actually end up identifying modes which are important from energy point of view, but are not important from dynamic point of view. Okay, so you may get a wrong information. So people in fluids community, they have been using the POD for quite long time. And the POD is basically, as I said, is a S and SVD, singular value decomposition. And they end up finding a modes which are actually important from dynamic point of from the energy point of view. But like phenomena like turbulence, which is an unstable phenomena, the dominant energy modes may not be actually the one which are causing the instability. There will be low energy modes which actually over a period of time actually causes instability, and those will not be captured when you do this POD. Okay, so to capture those kind of modes, or capture the what modes are actually more relevant from a dynamic point of view, instead of doing a POD, one could do DMD, which is this dynamic mode decomposition, which actually accounts for the fact that there is a temporal causal relation in this data, and the modes that you end up identifying from the DMD will tell you what are the most significant mode are from a dynamic perspective. What I mean by that dynamic perspective is that, because think about simple A matrix, right? So you have just x dot equals AX system. Now A has some eigenvalues, right? And assuming A is stable, there are some eigenvalues which are further in left half plane, they decay very fast. So those are not dynamically important because the transient actually decays much faster. But there are some eigenvalues which are close to j omega axis. Their response actually decays much slower. So those are actually more dominant. Right? So if I want to actually, if I want to do some model reduction of that A matrix, I would actually only pick those modes which have eigenvalues that are closer to j omega axis. And that's what you could do using method like this. That makes sense? I mean, there are a lot of words without writing, but I hope I was able to convey the meaning of it and the distinction between this SVD and the DMD, right? So, and what is the sort of the motivation for DMD? So the DMD was actually developed like independent of the Koopman things, but then people realized the connection of the DMD with the Koopman, yeah. So you can, so the lambda, once you find this A matrix, you can actually compute the lambda, which are the eigenvalues of the A. Those will be called the matrix of DMD eigenvalues. And then the W will be the corresponding eigenvectors. So as I said, this is sort of a very plain vanilla algorithm. I mean, there are various variants of this. Instead of looking at the doing the singular decomposition of the entire matrix, one can also do one can only preserve from a numerical computational efficiency point of view, you can only look at only dominant eigenvalues and so on and so forth. Okay. But that's the basic idea. Okay. Now the algorithm which is sort of comes through in spirit with the Koopman thing is what is called as the extended dynamic mode decomposition. The extended term here is because of the fact that we are not. So in this, if you think about it, in this case, we are actually just using the identity functions for lifting, right? Because we are really not lifting, because we are just working the same data. That is the same as saying I'm just using the identity function for lifting. So there is no lifting function involved. But now I could actually lift these functions, and that's where I could actually use a nonlinear observables to lift the data, and that's where the word term extended dynamic mode decomposition comes from. Okay. Any questions? It's also called EDMD. Okay. So again, in this EDMD, you assume you have a tuple of data, which is, let's say, xk and xk plus 1. Let's say k equals 1 to m, and then these are described as sk plus 1 equals t of xk. So you don't have access to the t, you just assume that, or you just assume that there is an underlying dynamical system from which this data is generated. So you have xk and xk plus 1, like a time series of data. Now what you do is that you actually pick some library of functions, which are the observables, right? So let's say if xk belongs to some Rn, you can pick a library of functions, observable functions, psi I from Rn to R, and then I will go from 1 to, let's say, D. Okay, you have D dictionary functions. So you can actually now put these all functions together in psi of x. So this is now becomes a vector valued function, so which is psi 1, psi 2 to psi of D, right? So this is basically the so-called lifting function. So D could be larger than or equal to n. Okay, so you are lifting in a high dimensional space. So rather than describing the evolution, so this is what was talking about. Now we are using a lifting function to go in a high dimensional space, and then try to describe the evolution of these observables rather than the evolution of the state themselves. Okay. Okay. So you have psi of x, and similarly you have so you have psi of psi of x, and then that oops. So these are dictionary functions. So we can now compute these functions on the data set, right? So these are just functions that you pick. Now you evaluate this function on your data point, which is xk, xk plus 1. So let's call capital psi of x. Now this is a matrix as psi of x1, psi of x2, dot, 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 psi of xm, xm. Okay. So these, each of the psi are the vectors, right? So this is now will be a matrix in D cross M, right? It will be a matrix in D cross M. And similarly, you can construct psi of x prime. So that will be psi of x2. So you just do a delay, psi of x3, psi of xm plus 1. Okay. Now you can again ask, what is the best matrix that can actually explain this data in the lifted space, right? This is my lifting function psi. So let's say if K is the matrix, K acts on psi of x should be equal to psi of x prime. What is the best K matrix I can actually pick? Again, this becomes a least square problem. Right? So you can write down this as minimize your k. I mean, let me write it down, and then I'll sort of give a caution. Okay. You see, I mean, I think I told you, right? I was when we did these examples, I was multiplying. So the way you think about this k, using that commutative diagram, was that you have this function space, and then there is a kappa here, which is the infinite dimensional. Then you go to this low dimensional space. In this case, is a d-dimensional space, because you're looking at this embedding, or you're looking at the d-lifting functions, and then you are constructing this matrix thing, right? And then this k is actually propagating the coefficients, not the functions. And to get the functions, you have to do a psi transpose that coefficients. But here, actually, so what k that you end up finding is actually a k transpose in this set, okay? Because I'm multiplying the functions from the right, whereas there I was multiplying the functions from the left. Okay, but that's a minor thing. Okay. So again, this we can get the solution of this as a least square problem as k star to be psi x prime psi of x pseudo inverse, right? Okay. And if I have to be precise, if I have to sort of stick to that notation that I use, then I should really call this as a transpose, right? Because this is here, the functions are multiplying from the right, whereas there, the functions have the notations I was used, the functions were multiplying from the left. So coefficients were multiplying from the right. So if you don't like, I hope you get the big picture. The small details actually, if you start working on some of the examples, I mean, you'll see the small difference. And that small difference could make a big difference, especially if you're not aware of this, right? Because instead of finding the right instead of finding the eigenfunctions of the k, you'll end up finding the eigenfunctions of the k transpose. And that will be actually the dual, okay? Because that will end up finding the eigenfunction of the Perron coordinate because of the duality. Instead of finding the eigenfunction of the Koopman, you end up finding eigenfunction of the dual operator, which is the Perron coordinate. So if you're not sort of aware of that, so but that's a detail, but it's a very important detail one has to sort of aware of. Okay. And again, this pseudo inverse is psi of x prime. Pseudo inverse will be psi of x transpose, psi of x inverse, psi of x transpose, right? So this is one like a very simple way of deriving. There are alternate derivations as well. Let me just write down that I could derive it, but I think yeah, I mean, I could try to derive it, but it's not uh, very illuminating. Okay, the derivation is not very illuminating. It's just basically a lot of bookkeeping. Okay, as long as you get this big picture, I think that's what is more important. So if you understand this, let me just give you another algorithm, and purely at the algorithm level, without actually deriving without actually giving you the math behind the algorithm. Okay, because that is, I think, much more popular one algorithm. And if I'll be giving you some code, and that code actually, that is what the algorithm is used, because it's more efficient compared to this. This derivation is easy to derive mathematically, but it's not very numerically efficient. The algorithm I'm going to give you, it's also easy to derive mathematically, but just as I said, it's not very illuminating. It's just a lot of bookkeeping, but it's more numerically efficient algorithm. So I'm just going to give you that algorithm for the EDMD because it's the most popular one and it's also efficient without giving the mathematical details. So what does that algorithm looks like? So algorithm looks like the following. I mean, it's just a two-line. So in that case, the K, the Koopman matrix, is given by the following formula. Is given by G pseudo inverse A. In fact, the pseudo inverse can be easily replaced with the inverse. because the matrix that we're dealing with is invertible, right? So pseudo inverse you use whenever the matrix is not invertible, but in this case, the G, so where the G is given by 1 over m psi of x, psi of x transpose, and A is given by psi of x, psi of x prime transpose 1 over m. Okay. So psi of x, what's the size of psi of x? Psi of x is d. Yes. So this, if you think about this, this is d times m, and this is m times d. So this is basically d by d. Okay, and d by d matrix, and this will also be a d by d matrix. Okay, and this matrix G, if your data set, if the lifting functions are linearly independent, if the data set is sort of sufficiently excited, the G matrix will be invertible. So you don't really have to take the pseudo inverse. So you can just simply take the inverse of this G. And as I said, I mean, there is a mathematical derivation of this. It's there in uh, multiple papers and things, but I'm not doing it. It's not difficult. Okay? So that's the alternate algorithm, and this is the one I will give the code for. Now, right? So once you have this K matrix, you can actually do the eigenvalues, eigenvectors. So K Wj equals lambda j Wj. I want to tell you one more important thing, which is actually kind of could be interesting. So now once you have these eigenvalues, eigenvectors of the K, the eigenfunctions, as we saw, are given by, or the approximation eigenfunction phi lambda of x will be of the form Wj transpose psi of x, where psi is the lifting function, right? Okay. So this will be the approximation eigenfunction using the eigenvalues obtained, and eigenvalues and eigenvectors obtained from this finite dimensional K matrix. Now there is concept of what is called a Koopman mode decomposition. Okay, some of you may have heard this, some of you may not. So what is this Koopman mode decomposition? And I think like it's a fairly simple idea, but I think it's very powerful, because I think some of the applications I'm going to talk about, I think this idea can be used very effectively. Let's say you want to actually, let me first talk about what is Koopman mode decomposition is, and then I'll tell you what is the use of this Koopman mode decomposition, right? So what do we have so far? So we have, like, the scenario is following. So we have a data, we took the data, we compute this, use this algorithm to compute the finite dimensional K matrix. We took this K matrix, compute the eigenvalues and eigenvectors from this K matrix. We use the eigenvalues, eigenvectors on the K matrix, and then compute the eigenfunctions, right? So that's what we have now. From the data, we compute the eigenfunctions, right? Now let's say I give you some new function, observable. We call that as observable, okay? Which is the function, which is a function of states. It's a scalar value function, or it could be a vector value function. Let's just say I have a scalar value function, call it g of x. Okay, so this is some function g of x I gave you. Okay, to put things in little more applied context, think of g of x as some density function, like probability density function. Okay, that is you have some initial mass distribution of initial point. Okay, and the g of x describes the distribution of the initial point in the state space. Okay. Now I'm going to actually tell you how to actually use Koopman to propagate this distribution of initial points forward in time. Okay? So what you could do is that you could say, what can I write this g of x in terms of the eigenfunctions of this Koopman operator? can I write this as some linear combination of the eigenfunctions phi lambda I of x for some coefficient alpha I. So basically what you're doing is that we're taking this function g and projecting onto the space which is spanned by the eigenfunctions phi lambda I of x. Okay, where alpha i's are the coefficients in the expansion. Make sense? Hmm? In fact, I don't have to stick to these eigenfunctions. I know if phi lambda I is eigenfunction, then what is also eigenfunction? Phi lambda I times phi lambda 2 is also eigenfunction, or phi lambda j is also eigenfunction, right? So I could actually use that algebra property of the eigenfunction, because these I may not actually be able to. So if I give you a very complicated function, this only the n eigenfunction may not be enough to give an optimal projection. So you may want to use more basis functions, right? So this phi lambda I, the eigenfunctions, are basically now used as the basis functions. And in fact, it doesn't have to stop here. I could use like phi lambda I, phi lambda j also as a basis function. Not only that, I could also use phi lambda I, phi lambda j, phi lambda k. And this can keep on doing this. I can just keep on doing till infinity. So I have from this d eigenfunctions, because I'm using the d lifting functions, I could construct infinitely many eigenfunctions, right? Right? So if I want to write that down mathematically, how will I write it down? Is that I could say alpha k. Now k is my some, not a scalar, but k is a vector, right? Right? And how should I write this? So I could write this as product, right? Phi lambda, phi lambda, lambda ki, I equals 1 to d, right? So I'm kind of, so this k here is like k1 to kd, right? I hope I'm getting the notations correct, but you get the essence of what I'm trying to do, right? So now these coefficients are not parameterized by a scalar, I mean not parameterized by one number, but these are parameterized by a vector, right? Because now I can take not only the one eigenfunction, but I could take a product of them. I could take like as many product as I want, right? So you could compute this, okay? But let's just, for simplicity, let me just stick to this, okay? Because this, what I'm going to do next, it will be easier to explain in this, right? Let's just take, I just use only the the d eigenfunction, okay? Now I want to understand how these functions evolve over time, okay? How these functions evolve over time. And this function could encode like the uncertainty in your initial condition, as I said, right? So there are a lot of problems in robotics, and especially in power system, where you are interested in understanding how does the uncertainty propagate, right? So you have some uncertainty initial condition, and you want to know how that uncertainty will flow forward in time. Okay, now this uncertainty can be encoded in G, and then I want to know how the G looks like, or if I make the Koopman operator acts on the G, how will that look like? Right? So that will be alpha I kappa phi lambda I of x. This is like forward propagation of the G function G. Now, what is, because this phi lambda I are the eigenfunctions, this simply becomes alpha I lambda I phi lambda I of x, right? This is this. Now, this is my, let's say this is G0, 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 G0. This is my G1 of x, right? Now, you can also do G1 this of x. And in fact, you could do something like n times step. So this becomes alpha I lambda I power n phi lambda I of. So what this tells you is that once I do this decomposition in terms of eigenfunction, propagation becomes almost straightforward, right? Because all you're doing is actually just multiplying this eigenfunction with this alpha I lambda I. So these are basically the modes, right? And what is the Koopman mode decomposition? This is basically what is called a Koopman mode decomposition, where you are actually decomposing any given function in terms of the Koopman eigenfunction. And the alpha i's are the projection, or alpha i's are the coefficients used in the expansion. Okay? These are called as the Koopman modes. Koopman modes of the observable G along the eigenfunctions of the Koopman operator. Okay? And this can be used for doing applications like uncertainty propagation. And in fact, you can also use this to compute in robotics. I think you are interested in understanding the reachable sets, like what all sets that you can actually reach um, given a control input and disturbance, what all sets that are actually reachable from any initial set. So you can actually use this to compute the set of all possibilities that you can have in the forward in time. Okay. Any questions? Yeah. So yeah. So let's say if you have phi lambda 1 times phi lambda 2, right? Then if you make the Koopman operator act on it, then the eigenvalues will be lambda 1 times lambda 1 plus lambda 2, right? Uh, that's what we discussed, right? So if you have k phi lambda 1 x equals lambda 1 phi lambda 1 x, and then k phi lambda 2 of x as lambda 2 phi lambda 2 of x, right? Then k phi lambda 1 phi lambda 2 of x will be phi lambda 1 times t of x phi lambda 2 times t of x, which is same as lambda 1 phi lambda 1 of x lambda 2 phi lambda 2 of x. Yeah, so it will be a product. So lambda 1 lambda 2 phi lambda 1 of x phi lambda 2 of x, right? So it becomes lambda 1 lambda 2 becomes the eigenvalue. Yeah. Yes. So yeah, we spoke about this yesterday. So now there are like two approximations that are happening if you think about it, right? So the one approximation is happening because you're using only finite lifting functions. And then the second approximation is happening because you have only finite data, right? So they have the d as the length of the basis and m as the length of the data. So so for a fixed d, one can show that the error uh, the Koopman operator that you're ending up approximating is a projection of the true Koopman on this finite dimensional subspace spanned by the d eigenfunctions. That is as far as the bases are concerned, or the lifting functions are concerned. Now, as far as the data is concerned, the error goes like 1 over square root of the m, where m is the data length. And that's is a very classic result because this is coming because of the least square problem. So in the least square, those are the error estimates, and those error estimates just carries over in this case. So so that's how you sort of so there are plenty of papers on this, but the one which is sort of the earliest one is by the Milan and Igor on convergence analysis of the extended dynamic mode decomposition. Now, in that paper, they didn't talk about that. I mean, there are no results on the how to deal with this finite like lifting functions, like what are the error convergence rates as far as the finite lifting functions are concerned. But now you can actually use the kernel methods where you're using infinite functions. So that problem of using finite basis no longer applies. So only it becomes a function of data length. And we have some papers on that where the convergence rates are sort of discussed with those things. Yeah. So this is as far as the discrete time things are concerned. Now you can also approximate these instead of approximate these operators, you can also approximate the generators, which is the continuous time. Uh, and the reason you want to do that is because I think in control problem, many times, I mean, for example, if you're dealing with like control affine systems, so control affine system has a structure. The discrete time system doesn't have any structure. I mean, you don't see a control affine structure in for discrete time system, or it's, I mean, you can have it, but it's not really useful. But the control affine structure is actually very useful when it comes to continuous time system. And that structure can be actually sort of effectively exploited when it comes to control design in the Koopman space for control affine system. Now, and that's why you maybe want to interested, maybe one would like to actually directly approximate the generator rather than approximating the operator, okay? The Koopman generator. And then the classic algorithm for approximating the Koopman generator is called GEDMD, G for the generator. So generator extended dynamic mode decomposition. Again, the idea is fairly, I mean, straightforward. It's not something which is fairly, complicated to understand. So that's what we will talk about. I'll at least give you some brief summary. So it's basically called as the generator extended dynamic mode decomposition. Called GEDMD for short. Okay. Now again, since it's a continuous time, instead of xt and xt plus 1 or xk and xk plus 1, what information you need is actually you need a derivatives information. So you assume that you have information about x, k, and like x k dot. So what is a k here? K is not a time anymore. K is just like a number of data points. Okay, and the data points, the causality is in the xk dot, not in the k. So you think about, you sample this whole space, like you sample the state space m points, and the k is the index for the points. Okay. Now, how do you get the xk dot? Xk dot you could perhaps get by some sort of again by discrete time approximation, numerical simulations, and things like that. But basically, xk dot is basically a surrogate for your estimated of xk dot, perhaps, right? So you can say that, oh, I have xk point, and then I can actually do some infinitesimal change around xk and get the xk dot. Okay? How do you get that? That's the numerical issue, but this is the information that you'll need to compute the GD. Okay. So let's say you have this information, xk dot, and then you have some like at the m points. Okay. I mean, there are a lot of these variants here in terms of, okay, where should I sample? How many samples I should collect? Should I sample uniformly, or should I sample randomly, or with what distribution I should sample? Should I sample along a trajectory, or should I sample along a not reflexive trajectories, and so on? So that, I mean, I could have a discussion on that as well. But anyway, I think this is what it is. Now, again, let me see if I have. Right. So I think, again, this also a sort of progress, just like what we did for the EDMD. So instead now, again, you have a lifting functions. So let's say you have this, what is the notation that we use? So we use, oops. Yeah, so we use psi. So we have this psi function of x again as like psi1 to some psi d of x. So these are the lifting functions. Now you define what you call as mm, uh, your psi of x at x, which is your psi uh, psi oops psi of x1 dot psi of x m. Okay, and now for the derivatives part, what you do is uh, you you define yeah. So you have this function psi. So now you define psi k uh, dot of x L. So here K is going from 1 to D, L is going from 1 to M. So L are for data points and K is for the functions, lifting functions, the number of lifting functions. You define this as partial psi K partial x j, j equals 1 to n. So n is the dimension of the state space, xl and xl. Okay. So this is basically your XL dot. Okay, this is basically your XL dot, which is this. Yeah, actually, I'm maybe using some. Let me just be consistent with the notations. So instead of XK, let me call it XL because L is I'm using it for the data points, and K is I'm using for the lifting function. Okay, so you have the lifting function psi, which is psi1 to psi d. Now you compute psi k dot. I mean, it's basically, I should call it as a definition, right, rather than computation. So this psi k dot is defined as partial psi k partial xj. Since you know psi k, I can compute the derivatives. I can evaluate the derivatives at the data point xl because I know xl. And then f tilde. What is f tilde? F tilde is nothing but the vector field, which I don't have information about, but I have the information about f tilde in the form of xl dot, right? And xl dot is the information. I have it right at the beginning, I'm assuming, right? So I have this information, which is xl dot for L equals 1 to M. So xl is used here, and xl dot is this quantity, f tilde, okay, which is the vector field. So that is how we compute, or I define psi k dot. Okay? Psi k dot is not is defined like this. So this is the definition. You see, with all these quantities on right hand side, I have the information about. Okay? So what I get is, so I construct this psi x at its end data points, and similarly now I define this psi x um, as this, which is psi dot of x1, psi dot of x2, psi dot of xm, right? And each of these are again the vectors, just like these are vectors, right? Where the individual elements are obtained from this formula. That makes sense? Good. Okay, so we start with data xl dot, where xl dot is approximated numerically. We have m data points. We pick this basis function psi1 to psi d, d basis functions. We construct this matrix psi x of x, just like what we did in discrete time, as psi x1, basically evaluating these lifting functions, that is m data points. We then define psi k dot as using the following right hand side, where all the quantities on the right hand side we have the information about. We know xl, these are data points. We know xl dot, right? And then we can compute partial psi k, partial xj, because I know psi k, right? These are the functions that I picked. So I know what partial psi k, partial xj are, right? And the summation is over the n, where the n is the number of, like, the state variable, right? The state space dimension. So once I get the psi k, I can now construct this big psi x dot as psi dot x1, where psi dot x1 is basically this vector with along for each of the basis functions. Right? Now I have this. So basically now what I want is, basically I want to find a generator which explains this matrix. So for lack of what notation we use, yeah. So we use the L, right, for the generator. So L, let's just, since we are doing the finite dimension, let me just use capital L instead of calligraphic L, where the L is for the generator. L times psi of x. So this is what you want to solve for. Again, this you can write it as a least square problem. Minimize over L, summation psi x minus L psi x, and then you get a least square solution for the generator. Okay. Okay. So your L star will again be psi x dot psi of x pseudo inverse. Right. So I also have the code for the GDMD algorithms. I can also provide you that, which you could use to compute this. Okay. Any questions? Now, I mean, this you can also use for these algorithms can also be used for approximating the Perron-Frobenius by just using a duality. Okay? Now, this Koopman is Perron-Frobenius is dual to the Koopman in a finite dimensional setting. That means that if the P is the matrix corresponding to the Perron-Frobenius operator, then P can be written as K transpose. Okay, because in the finite dimensional, the dual becomes transpose. Under the assumption that the basis functions that you're using is orthogonal. If the basis functions are not orthogonal, then you have to sort of normalize the P matrix to get you have to sort of normalize the Koopman matrix to get the P matrix. So basically what it means is that PF approximation, if the basis functions are orthogonal, if the lifting functions or the observables are orthogonal, orthonormal, then the finite dimensional PF denoted by P is given by P equals K transpose. Okay. If the basis are not orthogonal, then P will be G inverse K transpose G, where the G is the Gram matrix, right? And in fact, I think we defined the G in the past, which is, so G is basically 1 over M psi x transpose. This is the Gram matrix. So, I mean, I think there is beautiful interplay between the eigenfunctions and of the Koopman and the eigenfunctions of the Perron-Frobenius. And maybe when I give you the code, you can actually try it on a simple system like this, the van der Pol oscillator, right? So you know this van der Pol oscillator system has has a stable limit cycle and unstable equilibrium point, right? Now, um, uh, so the stable limit cycle is like if you take any initial condition for the van der Pol oscillator, everything basically converges to the limit cycle, right? Now, what you can do is that you can actually now compute the eigenfunction corresponding to the eigenvalue 1 of the Perron-Frobenius operator for the of the for the van der Pol oscillator. So you first you take a data. So this is what you do. You start with the van der Pol oscillator. You take the data, sample the data, use the algorithm to compute the Koopman, and then use this transpose or the second formula to compute the Perron-Frobenius, right? Now, you compute the eigenfunction with eigenvalue 1 for the Perron-Frobenius. What do you expect to see? What is the steady state dynamics of the van der Pol oscillator looks like? Where does everything eventually gets down to? On the limit cycle, right? So what will be the, what I told you, the Perron-Frobenius eigenfunction captures the steady state dynamic. So what do you expect to see in the eigenfunction? Where the eigenfunction will be supported on? The eigenfunction will be sitting where? It will be 0 everywhere, but it will be non-zero on the limit cycle. Right? It's a, I mean, since you're doing numerically, it will be sort of, there will be some region around the limit because it's all numerical. Because the function itself is actually it's not a function, it's a distribution because it's a measure zero set. But numerically, we'll see some region around the limit cycle where that function will be non-zero. Okay, but that's not the complete story. Now, if you look at the limit cycle is nonlinear. What does that nonlinear limit cycle means? So limit cycle is nonlinear. What it means is that there is also a temporal characteristic in the limit cycle. So if you look at closely at the limit cycle, what you will see is that limit cycle, the amount of time the system trajectory spent on limit cycle is actually non-uniform. What happens is that whenever it comes to two edges, I'll do a very bad job, but let me do it anyway. So if you look at this thing, so the limit cycle looks something like this, okay? And then in this region of the limit cycle, system trajectory spend more time. That means system trajectory actually slow down when it actually passes through the region. And here it actually becomes very fast. And again, it slows down here. Okay. So what it means is that in different region of the limit cycle, the system spend different amount of time. In this region, it spend more time because it slows down. In this region, it spend less time. In this region, again, it spends more time. Okay? Now, this non-uniform distribution of time is actually captured in the invariant measure. So when you look at the invariant measure, not only it is supported only on this region, but if you look at the colors of the the values of the eigenfunction. So if you construct a boxes around this, like, right? If you just think about, you box the whole region. So everywhere the eigenfunction will take a zero value, except in this small boxes which are covering the limit cycle. Okay. And in the boxes which are closest to the edges, the value will be very large. That is signifying the fact that system is spending more time. So the time average is equal to space average. This is basically ergodicity. So the eigenfunction with eigenvalue 1 of the Perron-Frobenius operator captures the time information as well. Although it's a spatial function, it captures the temporal information. Okay, and that's kind of very, I find it very interesting. And that basically comes from the ergodic theory saying that the time is space. So on this, the measure, so the system, to put it very, say it mathematically, the van der Pol oscillator system is actually ergodic with respect to the underlying measure coming from the eigenfunction with eigenvalue 1 of the Perron-Frobenius operator. Okay? Because with respect to that measure, time average equal to space average for any function. Okay? So the system is said to be ergodic if the time average is equal to space average, but that statement itself actually doesn't mean much. It's a very trivial statement, or it's like with that definition, every system is ergodic. Okay, that I mean, yeah, maybe this is sort of going a little tangent, but uh, if you if you when the system is meaningfully ergodic, if only if the underlying measure actually is has some nice property. It's in this case actually the measure is actually a singular measure because it is only supported on the limit cycle, but it's actually what is called as a physical measure. That is a measure which can be actually physically seen. Okay. For example, if I give you a system x dot equals x dot equals x system, what is that system? It has a x equal to 0 is a unstable equilibrium point, right? It's an unstable equilibrium point. So if I give a distribution of initial condition, what will happen? They will just go to infinity, right? But that system is also ergodic with respect to the delta measure, but the delta measure is actually not physical, okay? Because you cannot see it. On the other hand, if you take x dot equals minus x, that system is also ergodic with respect to the delta measure, but that measure is actually physical because you can actually see it. When you simulate the system, you actually everything converges to the equilibrium point. So delta measure there, while it is ergodic, but it's also physical. For x dot equals x, the delta measure is ergodic, but it's not physical. So you can always make a delta measure ergodic. It may be physical, it may not be physical. So the most meaningful ergodic system, I mean, from practical point of view, is the measure is not only ergodic, but it's also physical. That means it's something that you can see in simulation. By physical, I mean you can see in simulation. You can realize in simulation. In this case, the measure which is supported on the limit cycle is actually physical because you can see it. When you simulate a system, you will see that system is actually converging to that measure. Okay. So anyway, that's sort of a tangent of to connection of this, because these operators classically has been used a lot in ergodic theory, but recently they are now becoming more popular in many of this in like all this data driven analysis and control design, right? But these actually operators have a long history of studying these in the ergodic theories. Yeah. Yeah. So that's it. It captures that information. Occupation measure, exactly. And the occupation measure is what is actually very useful from practical point of view. I'm going to talk about in robotics when you want to design safe controllers, because occupation can be directly connected to the safety. If I want to keep certain things safe, I want to have zero occupancy in that. So you can actually look at a dual. So that's actually a dual perspective to this safety from the occupancy. And even the control problem could be actually posed in terms of occupancy. I mean, so anyway, I think I'll if I can take some questions. If not, then I'll stop.